Hello class, this is a video tutorial on related rates of change. I want you to consider the volume inside of a spherical balloon. So let's just hypothetically say we have a perfectly spherical balloon. Once it is punctured, it will begin to lose air, meaning it's going to lose volume, and so lose surface area as it deflates. So here's our perfectly spherical balloon. We poke a hole in it, it will start to lose air. And as it loses air, it's also going to get smaller and smaller, and eventually it's going to be completely deflated. This is one example of related rates. The reason for this is, while both the volume and surface area are decreasing, the rates of each are different, but they affect one another. You'll see more examples of this in action as we do some examples. But the general idea we're going to be working with is as follows. If y is related to x, meaning we have y equals some function of x, and x is related to t, likewise, x equals some function f of t, and often t is going to be time, so it could be seconds, minutes, hours, but it doesn't always necessarily need to be time, but it often is. The instant rate of change of y in relation to t uses the chain rule dy dt, so that's the instant rate of change of y against t, is equal to dy dx times dx dt. A very simple way of understanding this is if you consider these as fractions, you can cancel this denominator with this numerator, leaving us with dy on dt. That isn't necessarily the true mathematics behind it, but that's a simple way to understand it for now. So let's take a look at this in an example. So let's say we're given y equals this function of x, and the rate of change of x being 5. Let's find the rate of change of y against t. So just to give this some context, is let's say we have y being volume or area. Okay, let's say it's area. So y is area. X is the length of one of the sides, so x equals the length of one side. And the length of the side is increasing by 5 units per second. Okay, what is the rate of the area increasing by when x equals -2, for example? Okay, so notice how if we try and find the derivative of y, so let's take a look here. Let's say we have y and we want its derivative. Dy on dx equals 4x minus 3. Notice how this isn't the rate of change of y against time. It's the rate of change of y against the length. We want the rate of change against time. So in order to do that, we're going to take, so we want dy on dt. We can find this by taking dy on dx, multiplying it by dx on dt. From here, dy dx is 4x minus 3, so dy dx is this expression, and dx dt is equal to 5. So this times 5. So we can say now dy on dx is equal to 20 minus 20x minus 15. So this is, sorry, I made another mistake. That's dy dt. There we go. So this is the rates of change of y against time, no longer against x. So from here, we can say now that the rate of change when x equals -2, we can find that by simply substituting it into our dy dt. That will give us 20 times -2 minus 15. That's dy on dt equaling -40 minus 15 is -55. So when x equals -2, the rate of change of y against time is -55 something per second. Okay, so I hope that gave you a basic insight into how we might apply related rates of change in a very simple way here in this example. There's going to be 4 more examples for this, and it'll hopefully make more and more sense as we do more examples here. I hope to see you in the next video. Best of luck.